start out with any questions. All right. Unless I missed it, then chime up again, but pick up sort of where we left off. Yeah, we're going to be doing some more letter stuff all over the board again. Not for you to just be able to spew it back later, but again, to see where some of the stuff comes from. So we'll start out with speed. What is the formula for speed?
Distance over time?
Yes. So if something is traveling around in a circle, what is the distance? That would be well, I guess the angular displacement. What about distance though? That's the one I'm looking for. Circumference. It's basically the circumference of a circle. So if this is some radius r, then this would be 2 pi r. Actually, could I see somebody's notes too from last time? We went from there into the black hole. Okay. All right. And the time it takes for something to go around in a circle, or for something that's repetitive motion, so perhaps it's going around in a circle several times. And I think this is going to go off again in a moment. All right. So what's it called for the time it takes to go around once?
Revolution?
The time to do one revolution. I guess how would you define revolution? Is the act of going around? It would have been part of the lab that is, I guess, doing right. Or the symbol. Yeah. And spoilers, if someone's about to do it, you can just shout it out right now. All right. It's called period. So the amount of time it takes to go around once is the period. All right, so let's just do a quick example here, and you did it in the lab, but let's say you're traveling in a circle with a radius of 5 meters, and it takes 3 seconds to do it. What is the speed?
4, 7, 2. No?
7, 2? Yes. All right. So that's how fast it is going. If it's traveling in a circle at a constant speed, is it accelerating?
Yes,
Why?
because it's changing direction.
Yes. And what is that acceleration called? If you have your lab sitting there, you can look at the title and the keyword is there, right there. Yeah, the acceleration would be centripetal acceleration. All right, so they're experiencing centripetal acceleration, which I abbreviate as A sub C. So centripetal. That second word there is acceleration. Someone got a little overexcited on the E there. And there is a formula for centripetal acceleration. And what is the formula for centripetal acceleration?
V squared over R.
That is one of them, yep. V squared over R, and that's the one that we really care about here. It could also be omega squared R, where omega is the angular speed. So for the lab, we did V squared over R. If we took the angle into account, we would have, it's actually more convenient to do omega squared R if you take the angle directly into account in that lab, which we did not do. All right, so if something is traveling in a circle, I know F equals ma, or I trust that it is, because if F does not equal ma, then, well, that's the whole foundation of this course, and it would all be a lie. So whatever the total force is, and again, this is total force. So something traveling in a circle, that total force is equal to the mass times centripetal acceleration for something traveling in a circle, which would be mv squared over r. And I know speed is just 2 pi r over the period, so right there. So instead of v, I'm just going to pop that in here, so I have m times 2 pi r over t squared over r. So I'm going to square everything inside the parentheses here, so this is mass times 4 pi squared r squared over t squared over r, which can just be simplified down into, well, that r cancels out with one of those, and I'm left with m 4 pi squared r over t squared. Okay, pause and let that sink in, and also for people to ask questions about how I did what or why I did what.
Is that a square over the R?
That's a square over the r, but I then
Okay.
canceled it out with that r right there.
Okay, gotcha.
So it was a square that went poof. And I guess, Joanna, I'm getting farther and farther away from you. You okay in seeing this?
Yeah.
Okay. Any other questions? All right, so this is sort of generic stuff right here. So let's actually make it something, a more specific situation. Earth. No, actually, let's make it the sun. The sun. Our sun. And planet. or actually anything going around the sun. What is the force that keeps the planet going around the sun? The answer is not magic.
Gravitational force?
Yeah, gravitational force. So I have this gravitational force pulling the planet towards the sun, which makes it go around the sun. If that gravitational force suddenly disappeared, what would the planet do?
Stay still.
No, would not stay still.
Float off. Would float off.
Depends which way?
Um,
Would it, I mean, shoot off like that? Is that what you were suggesting?
Look at it that way, yeah.
Or, so that way is, no, you're saying no. Are you saying that way?
Kind of, yeah.
Kind of, which way are?
Yes, that
Okay. Okay, so you're gonna stick with that? Remember when I was slinging the stopper around my head, it sort of went in a straight line as soon as I let go. It should actually shoot off like that.
I wasn't thinking about the fact that it was traveling in a circle.
Oh.
I think I'm thinking of it more literally. Would it, like, there's no atmosphere or gravity in space.
Well, there's gravity in space.
Between planets.
There's a,
Objects.
right, so
I'm sorry.
there's a gravitational pull between any two things with mass. So there is a gravitational pull between the planets, but the sun is so huge that it's the dominant force. So if the sun suddenly disappeared, then planets would travel close enough to a straight line. There is some influence by the other planets, so it probably would wobble a little bit. I did a scattershot approach from what I was hearing. Did you want to formulate a question?
No, I thought it would stay still, just because there's nothing affecting it if the sun wasn't there.
But Newton's first law of motion. If nothing's affecting it, it's gonna keep doing whatever it's doing. So since the Earth is already moving, it would continue to move. It just wouldn't bend. And remember, if the sun suddenly disappeared, we wouldn't know about it for another 8 minutes. I wonder at what point we'd freeze to death. Oh, anyway. All right, so the force due to gravity. So we can take this situation and we can just say, well, that's the force due to gravity for this case right here. Can't really use mg particularly well. We have a formula for the force due to gravity, and that one indeed was in what we did on Monday. And what is the formula for the force due to gravity? The general case. You would make me weep tears of joy if you could do it in unison right now.
Big G, mass 1 minus mass 2 over r squared.
You've got a straight mark there.
Okay.
Isn't it just mass 1, mass 2?
Yeah, it's times, not
Times
minus.
mass 2.
Over r squared. And so the two masses are the two masses involved here. So in this case, I'm gonna replace 1 and 2 with s and p for sun and planet. This radius is the center to center distance. In other words, it's the radius of the orbit. And that's gonna be equal to what we have over here, and that's the mass of the planet times 4 pi squared r over big T squared. We can consolidate some. First off, what can I get rid of? And so now I'm gonna consolidate. What I'm gonna do, because I know where I want to be on this, I'm gonna take this r squared and I'm gonna multiply both sides by it. In other words, bring it up over here. And I'm gonna take the 4 pi squared and I'm gonna move that down there. Purely from a pure math point of view, what I'm officially doing is multiplying by r squared over 4 pi squared. But, so what I end up with on the left-hand side is big G mass of sun over 4 pi squared. And on the right-hand side, I have r squared times r, which is r cubed, over t squared. And that's where I wanted to get. And I'm sure you're looking at that going, oh man, that's just so incredible. So questions before we talk about why this is so incredible? All right, so why this is so incredible is this applies to anything orbiting our sun. Now we did assume a circular orbit, which is sort of a not too bad estimation. It's not as exact as we could get. However, we can now figure out what the mass of the sun is. G is a constant, 4 is a constant, pi is a constant, so the math people tell us. Mass of the sun, relatively constant. So if I know the orbital radius of any planet, and I know how long it takes any planet to go around the sun, I can calculate what the mass of the sun is. Well, it just so happens, there is one planet where I do know how long it takes to go around the sun. And what planet is that? And how long does it take?
Earth.
And how long?
36
Okay. So let's take the Earth. So the period is 365 days. Let's bring leap year into it, so 2.25, slightly better estimate. Days. Of course, we want to get it into seconds. So how many seconds in a day? Some people know it. All right. What do we know? If I want to get days to seconds, what do we know?
There's 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute.
60 minutes per hour, and then 60 seconds per minute. So minutes cancel out, hours cancel out, days cancel out. All right. Somebody just.
86,400 seconds.
Seconds per day. All right, so if we multiply 365.25 times 86,400, what do we get?
31,557,600.
Is that 31,557,600 seconds? All right, so that's the number of seconds in a year. What about the orbital radius? Now, that's not something that would normally know. No, there is actually a unit that the astronomers first came up with. They figured there's some average distance there, and that's what an astronomical unit is. So R is 1 astronomical unit, which really doesn't help us here, but if you hear the term CAU or hear someone refer to astronomical unit, it's just that average Earth-Sun distance. We can actually find it. We could find it if we had good enough equipment. All we need is, some sort of flattish surface, and we have a distant object. You stand here and you look to see where this is. You stand here and look to see where this is. If you know that angle and this distance here, you can predict how far away the sun is. Or you look up in the back of the book. Radius of Earth's orbit, 1.5 times 10 to the 11th meters. So let's do some math. Some more calculator fun. The marker over here. Rearranging that slightly, I did put it in that form for a reason, and I have not gotten to the reason yet. But the mass of the sun is going to be r cubed over t squared times 4 pi squared over big G. So that is 1.5 times 10 to the 11th meters cubed times 4 pi squared over the period, which was 31,557,600 squared times G, which is 6.67 times 10 to the negative 11th. If someone with a calculator, or several people with a calculator, be so kind to calculate that.
$8 billion.
That doesn't seem right.
Oh no. Maybe my pen dots are wrong.
Hold on just a second.
I got 2.068 times 10 to the 30th.
Okay, that
2.0648 times 10 to the 30th.
that seems much closer. And again, I know what the answer is supposed to be, so when that's close to it. Anyone else get this? No one else got this? For those who have not worked it out right here, just please make sure that you get answers somewhat similar to that before the quiz. Please make sure you have parentheses in the right spot.
Yeah, no, I got that.
Now you got that, okay.
I have 2.005, but yeah.
005?
To the 30th.
So you're saying Rachel doesn't know what she's talking about?
No, I'm just, maybe my numbers or something.
The back of the book has it at 1.99 times 10 to the 30th. It's a 30 there. What units? could stick in the units into the stuff that you just calculated and do it that way. So that was meters cubed on top, and on the bottom, that was seconds squared, and this is a Newton meter squared per second, Newton meter squared per kilogram squared. I don't know if that helps you or not.
Could you cancel out the meter squared?
All right, so that goes away, and then two of those go away, so we're left with just m on top. And we're dividing by a fraction here, so it's multiplying by the reciprocal, so that's a meter kilogram squared per second squared Newton. It can be reduced further. So what's a Newton?
Meter squared?
A little bit off. Kilogram times meter squared is the unit of
Over
moment of inertia.
over seconds. Kilogram times meter over seconds.
That's momentum. No, that's not quite a Newton.
Kilogram times meters over second squared.
That's it.
Oh.
Mass times acceleration, kilogram times meter per second squared. So this is a meter kilogram squared over second squared times kilogram meter over second squared. Now what can we get rid of?
The second squared and,
Yep.
so would it just be kilograms?
Yes, it would. We found the mass of the sun, it's kilograms. That meter cancels out with that, and that cancels out with one of those. It is just kilograms. Excuse me. I would be concerned, except I've had a cough pretty much since January. I guess that's a different concern. All right. So we can now we have a way of finding the mass of the sun. But questions before I get back to why I put it in this form. All right, so in the 1500s, could be off of that. In the 1500s, a guy named Johannes Kepler took a whole bunch of data, precise astronomical data, and tried to come up with rules of planetary motion. And he came up with 3 rules. Rule number 1, planets travel in ellipses. Which is a pretty amazing observation. If you think about it, we're all orbiting the sun, so we actually don't see the other planets do the full orbit. What we see is, that sun here. We're traveling around like this. Another planet is farther out, is traveling around like that. As we approach it, it looks like it's coming towards us. And then we pass it, and then, coming towards us, and then we pass it, and it looks like it continues to go in that direction. So it looks like it's going backwards to some extent. There are other times where it looks like it's going this way, and then it goes backwards. I believe that's called in retrograde. So he's making these observations, all basically a moving observer relative to the sun, looking at other things that are also moving relative to the sun. And he comes up with this idea that they're traveling in ellipses. Now, an ellipse, if I take 2 points, so just imagine I have 2 points here, and imagine I've got a nail stuck in there, and I take a piece of string, and I dangle the string between the 2 points. I then take a pencil, and I straighten out the string so that the lines, so that the string is tight around my pin here, and then I just start moving so that the length from here to the pin to the other point is always the same. So when over here, the string just stretches. If you trace out that path, that's an ellipse. These points here are called each one's called a focus, or plural foci, or foci. I guess if you're doing ancient Latin or more modern Latin pronunciation. And so he figured they travel in an ellipse, and the sun is at one of the foci. Now, generally when I draw ellipses, I draw more like the squashed circle. In reality, the Earth travels in really close to a circle. It's a little bit off of that. It is an ellipse by definition, but it's not so extreme. Pluto's the most extreme. And that's why they kicked it out of the club. And for, at least within my lifetime, this is 2020, if you were born in the mid-90s, there was a time when Pluto was actually closer than Neptune, for about 8 years. 2. I think I have these in the right order. For some reason, Kepler's laws don't sink in as easily as Newton's laws. The second one is the fact that if you look at all the planets going around the sun, that if you take the orbital radius and you cube it, and you divide by the orbital period squared, that's equal to some constant for all the planets going around the sun.